It is April 1st, 2026. The Florida coast is painted in that particular amber light that exists only in the last hour before sunset. The kind of light that makes everything look significant, as if the atmosphere itself knows something extraordinary is about to happen. A crowd of hundreds of thousands of people has gathered on beaches, on rooftops, on lawn chairs in Titusville Park across the Indian River from Kennedy Space Center. They've been arriving for days. Some of them drove from across the country. Some flew in from other nations. They brought their children. They brought their parents. A few of them, veterans of the Apollo era, came to see something they had almost stopped believing they would ever see again. At Launch Complex 39B, the same pad that sent Apollo 10 and the crew of Apollo 17 to the moon a half-century ago, the same pad that the space shuttle used 46 times over 3 decades, stands the Space Launch System. It is 322 feet tall. It weighs 5.75 million pounds. Every gram of it is pointed up. At 6:35 in the evening, Eastern Daylight Time, the 4 RS-25 engines ignite simultaneously. 7 seconds later, the twin solid rocket boosters fire. The combined roar generates 8.8 million pounds of thrust, more force than any rocket currently operating on this planet, and the sound hits the crowd at the speed of sound, a fraction of a second behind the light, a pressure wave that you do not hear so much as feel in your sternum, in your teeth, in the backs of your hands. The machine rises, and aboard it, inside the Orion spacecraft named Integrity, for human beings who have trained for years for this exact moment watch their world fall away beneath them. For the first time in 53 years, humans are leaving the safety of Earth orbit behind. Let that land. 53 years. That is not a generation gap, that is a civilization gap. In 53 years, the entire internet was born and grew to encompass nearly all of human knowledge. The Soviet Union rose to its peak and collapsed entirely. The personal computer went from science fiction to something everyone carries in their pocket. 3 generations of children grew up looking at the moon from their backyards and wondering, the same wondering their parents had, and their grandparents had, when we would go back. The answer, as of this recording, is we already have. And that changes everything. To understand why Artemis II is the mission it is, and why it matters the way it matters, we have to go back. Not just to the 1960s. We have to go back further than that. We have to go back to the most fundamental truth about the species that built the rocket. Human beings are exploratory animals. This is not a metaphor. This is not a poetic sentiment. This is biology, behavioral genetics encoded into our lineage over hundreds of thousands of years of evolution. The drive to cross the next ridge, to sail past the horizon, to climb to the top of the mountain not because you need to be there but because it's there. These impulses carried our ancestors out of East Africa approximately 70,000 years ago, across land bridges into continents that no human had ever stood on, across the open Pacific Ocean in hand-built wooden boats using stars and wave patterns for navigation, to the poles of the planet, to the deepest trenches of the ocean floor, and finally, in the extraordinary compressed window of the mid-20th century, to another world entirely. The moon landings were not a fluke. They were inevitable. The only question was timing. But timing, it turns out, is everything. The 12 human beings who walked on the moon between 1969 and 1972 did so because of a specific concatenation of political, technological, and economic forces that will likely never be exactly replicated. The Apollo program was not, at its core, an exploration mission. It was a geopolitical statement. President Kennedy stood before Congress in May of 1961, less than a month after Soviet cosmonaut Yuri Gagarin had made the United States look like a second-rate space power by becoming the first human in orbit, and he made a challenge that was really a demand disguised as an aspiration. He said, "Before the decade is out, we will land a man on the moon and return him safely to Earth." What that speech actually said, stripped of the inspiring rhetoric, was this: we are in a Cold War with the Soviet Union, the stakes are global influence, and we cannot afford to lose the space race. The moon is the ultimate trophy. We will win it at whatever cost it requires. The cost was enormous. At its peak, the Apollo program consumed more than 4% of the entire federal budget. In inflation-adjusted 2025 dollars, the total cost of Apollo through the final landing was approximately $300 billion. At the height of the program, NASA employed some 400,000 people directly or through contractors. More than 20,000 companies were involved in building the hardware. For the specific purpose of getting Americans to the moon before the Soviets, the program was a triumph of human organizational capacity that has never been surpassed. In 8 years, NASA went from having never put a human in orbit to landing 2 of them on the lunar surface, with all the hardware, infrastructure, training, and operational capacity that required. And then they went back 5 more times. 12 men walked on the moon. They collected 842 pounds of lunar rocks. They deployed seismometers and laser-ranging retroreflectors. They drove electric rovers across the lunar surface. They hit golf balls. They left plaques that read, "We came in peace for all mankind." And then, on December 14, 1972, Commander Gene Cernan climbed up the ladder of the Apollo 17 lunar module for the last time. He paused on the bottom rung and said, as if he knew it needed to be said and meant forever, "We leave as we came, and God willing, as we shall return." He stepped off the moon, and humanity did not return for 53 years. Why? This is the question that haunts space exploration history. Not how did we go, but why did we stop? The answer is both simple and complicated. The simple version: Apollo won the race. Once Neil Armstrong planted the American flag on the Sea of Tranquility on July 20, 1969, the political objective was achieved. The Soviet Union never sent a human to the moon. The ideological statement had been made, loudly and unmistakably, before the entire world. And without the race to win, the political will to sustain the enormous expense of lunar exploration evaporated with remarkable speed. 3 completed Saturn V rockets sat unused. They are now in museums. 3 Saturn V rockets that could have taken 6 more crews to the moon ended their lives as static exhibits for school children to stand next to on field trips. The complicated version involves the specific dynamics of mid-20th century American politics, the Vietnam War, the social upheaval of the late 1960s and early 1970s, a gradual shifting of budget priorities, and a failure at the institutional and political level to articulate what human space exploration is actually for when it's not for winning a geopolitical contest. What followed was a strange kind of limbo. NASA still existed. NASA still sent humans to space on Skylab and then on the Space Shuttle for 30 years. The shuttle was a magnificent vehicle in many ways, capable of deploying and retrieving satellites, carrying the components of the International Space Station into orbit, serving as an orbital laboratory. But the shuttle was fundamentally a low Earth orbit vehicle, 250 miles above the surface of the Earth, still well within the protective cocoon of Earth's magnetic field, still dependent on emergency return capabilities that required being close to the planet. The moon is 250,000 miles away. The shuttle's ceiling was roughly 360 miles. The distance between those two numbers is the distance between a backyard and the horizon. Between 1972 and 2026, no human being traveled more than about 360 miles from the surface of the Earth. Every orbit, every space shuttle mission, every International Space Station crew rotation, all of it happened within a bubble that, on a cosmic scale, is barely distinguishable from the surface. For 53 years, humanity hugged the coast. The return was never going to be simple. The political will required to commit to deep space exploration without the existential urgency of the Cold War is a much more fragile thing than most people realize. NASA tried multiple times during those 5 decades to build new deep space capability. The Constellation program, initiated in the mid-2000s, aimed to build a new lunar landing architecture. It was canceled in 2010. The Space Launch System and Orion spacecraft, the hardware now carrying Artemis II, grew in part from Constellation's ashes. The Artemis program was formally established through Space Policy Directive 1, signed by President Trump in December 2017. Its stated mission was different from Apollo's in one crucial way. The goal was not just to return to the moon, but to build a sustainable presence there. Not a flags and footprints mission. Not a sprint followed by cancellation. A sustained campaign with international and commercial partners, using the moon as a proving ground for the technologies and operational knowledge needed for an eventual human mission to Mars. The target was originally 2024, then 2025, then September 2025, then February 2026, then April 1st, 2026. Every delay was real and was earned. The Orion spacecraft's heat shield showed unexpected erosion after the Artemis I uncrewed test flight in 2022. Engineers spent months analyzing failure modes and risk margins. Hydrogen leaks plagued the launch vehicle during wet dress rehearsals in early 2026. NASA postponed launch opportunities in February and March to make last-minute repairs. And this is where responsible spaceflight lives. In the delays. In the decision to not launch when something looks uncertain. In the culture that says, "We will not risk a crew because we are impatient." The 4 astronauts who climbed aboard Orion on April 1, 2026, knew this. They had watched the program delay. They had trained for years. They had entered quarantine on March 18th. They had waited, and when the window opened, they were ready. Now let's talk about the machine that carried them to the moon. Because the Space Launch System deserves a proper introduction, and it will not get one from the people who think it's too expensive or takes too long between flights. The critics may have valid points about economics, but the physics does not lie. The SLS Block 1 configuration stands 322 feet tall, just about 100 meters. As a point of comparison, the Statue of Liberty stands 305 feet, including her pedestal. So this rocket, standing on the pad at Kennedy Space Center, is taller than the most famous monument in American history. The Washington Monument is 555 feet. The SLS doesn't quite touch that. But if you put it on Fifth Avenue in Manhattan, it would be the tallest structure on most blocks. Its total mass at launch is approximately 5.75 million pounds. More than 726,000 gallons of superchilled liquid hydrogen and liquid oxygen are loaded into the core stage propellant tanks. The liquid hydrogen is stored at -423 degrees Fahrenheit, just 20 degrees above absolute zero, the coldest temperature possible in the universe. Managing propellants at those temperatures in large quantities in a rocket that needs to also carry humans safely, this is engineering at the absolute frontier of what the species can do. The 4 RS-25 engines on the core stage are perhaps the most tested large rocket engines in history. They are evolved versions of the Space Shuttle main engines, which flew on 135 missions over 30 years without a single engine failure during flight. Each one generates approximately 418,000 pounds of thrust. Together, the 4 RS-25s produce about 1.67 million pounds of thrust. That's significant. But the RS-25 engines don't provide the majority of the thrust at liftoff. The twin solid rocket boosters do. Each solid rocket booster stands 177 feet tall. Each one weighs about 1.6 million pounds. Each one generates 3.6 million pounds of thrust at ignition, roughly equivalent to 25 commercial airliners firing at absolute maximum throttle simultaneously. 2 of them together provide more than 7.2 million pounds of thrust. When you add the 4 RS-25 engines, you get the total liftoff thrust of 8.8 million pounds. The Saturn V, for comparison, produced approximately 7.6 million pounds of thrust at liftoff. The SLS is more powerful than the most powerful rocket in human history as of the Apollo era, by about 16%. The solid rocket boosters provide most of the rocket's thrust for the first 2 minutes of flight. Then they burn out, separate, and fall away. The core stage continues burning for about 8 minutes total before its engines shut down and it separates. By that point, the spacecraft is in a highly elliptical orbit, ranging from about 185 kilometers at its lowest point to roughly 2,200 kilometers at its highest. 5 times higher than the International Space Station at peak altitude. Then the Interim Cryogenic Propulsion Stage, the ICPS, essentially a specialized upper stage, takes over for a brief burn to circularize the orbit and then later for the all-important translunar injection maneuver. On day 2 of the mission, the ICPS fired its RL-10 engine to raise the spacecraft's orbit, and then the Orion's European Service Module engine took over for the translunar injection burn. The ESM main engine provides 6,700 pounds of thrust. Enough, NASA notes, to accelerate a car from 0 to 60 miles per hour in about 2.7 seconds. It burned for 5 minutes and 50 seconds. And when it shut down, the Orion spacecraft, with its 58,000-pound mass, was no longer in Earth orbit. It was on its way to the Moon. The Orion spacecraft itself is worth a detailed examination, because it is not simply a scaled-up Apollo command module. It is a fundamentally different vehicle for a fundamentally different mission era. The Orion crew module is 16.5 feet in diameter, larger than the Apollo command module's 12.8 feet. It has roughly 316 cubic feet of habitable volume. For 4 people on a 10-day mission, that's about 79 cubic feet per person, approximately the size of a large walk-in closet. This is not spacious living, but it is more than the Apollo crews had, and it is configured with modern ergonomics, better life support architecture, and sleeping arrangements that are more than just sleeping bags strapped to the wall. The primary flight computers use modern processors running flight software that would have seemed like science fiction to the Apollo engineers who worked with kilobytes of memory in the guidance computers that took humans to the moon in 1969. The display and control interfaces used large touchscreens rather than discrete switches and dials, though there are still physical backup controls for critical functions. There are nearly 1,200 sensors aboard the spacecraft feeding data to 7 miles of internal cabling. The Life Support System, the Environmental Control and Life Support System, or ECLSS, is a full operational system capable of supporting the crew for the entire mission duration. This is worth emphasizing. Artemis I, the uncrewed test flight in 2022, flew without a fully operational life support system because there was no crew to keep alive. Artemis II is the first time the complete system has been tested in the actual deep space environment with actual human bodies generating the carbon dioxide and moisture and metabolic byproducts that the system has to handle. Testing a life support system on the ground tells you how it performs in 1 gravity, controlled temperature, known atmospheric pressure conditions. Testing it in deep space where radiation levels are different, where temperature differentials between sun-facing and shadow-facing sides of the spacecraft are extreme, where there is no convenient abort to a nearby planet, that test is categorically different. The data from Artemis II will directly shape every life support decision made for every subsequent mission. The Orion heat shield deserves its own paragraph because it was the source of significant pre-mission anxiety and extensive engineering analysis. The heat shield is 16.5 feet in diameter, the largest ablative heat shield ever built for a crewed spacecraft. It uses a material called avcoat, a foam-like ablative compound embedded in a honeycomb structure that is designed to burn away during re-entry, carrying heat energy away from the spacecraft in the process. The science of ablative thermal protection is almost counterintuitive. You survive the heat by controlled burning. The shield consumes itself to protect what's inside. When Artemis I returned from its lunar trajectory and re-entered Earth's atmosphere at approximately 25,000 miles per hour, post-flight inspection found that the avcoat had ablated, burned away, in patterns that were more irregular than the models predicted. Some areas showed more material loss than expected. This triggered an intensive engineering review, an independent expert panel, months of analysis, and ultimately a decision to proceed with Artemis II using the existing design, with documentation confirming that the underlying structural integrity of the capsule would be maintained even under worst-case conditions. Design changes addressing the specific permeability issues identified in the avcoat are being implemented for the Artemis III heat shield. But for Artemis II, with its shorter skip re-entry profile, the analysis concluded the risk was acceptable. The decision to fly was not taken lightly. Space history has been written in the blood of programs that allowed schedule pressure or political pressure to override engineering caution. The Columbia tragedy, the Challenger disaster, the Apollo 1 fire. Each of these catastrophes had warning signs that were visible in retrospect and sometimes visible in real time, but that were set aside in favor of proceeding. NASA's post-Columbia culture of safety, built on the recommendations of the Columbia Accident Investigation Board, is designed precisely to prevent the repetition of those failures. The heat shield decision went through every level of review that culture demands, and the conclusion was fly. Now let's meet the people inside the spacecraft. This is perhaps the most extraordinary aspect of Artemis II as a cultural document, as distinct from its technical achievements. The 4 astronauts who are right now, as of this recording on April 5, 2026, traveling toward the moon represent a different version of humanity going to the moon than the one that went before. The 12 Apollo moonwalkers were all American, all male, all military test pilots, all white. This was not a coincidence. It was a product of the specific social and institutional context of 1960s America, where the military test pilot pipeline was the only credentialing system NASA trusted to select astronauts, where women were excluded from that pipeline by institutional policy, where racial segregation was still recent history. The men who went to the moon were extraordinary individuals, brilliant, courageous, technically masterful. But they represented a narrow demographic slice of the human species, because the program was built in an era that was narrow in those ways. The Artemis II crew represents something different. Commander Reed Wiseman, 51 years old at launch, a U.S. Navy test pilot with over 2,500 flight hours in more than 40 aircraft types, including the F-14 Tomcat, F-18 Hornet, and F-22 Raptor. Wiseman was selected as a NASA astronaut in 2009, flew to the International Space Station in 2014, spent 165 days in orbit, including nearly 13 hours of spacewalking, set what was then a station record of 82 hours of scientific research in a single week, and became the first astronaut to use social media extensively to document his experience in space for the public. He served as chief of the NASA Astronaut Office from 2020 to 2022. He is, by any measure, one of the most technically accomplished and publicly communicative astronauts of his generation. As commander of Artemis II, Wiseman sits in the left seat, the captain's chair. In theory, the flight is automated unless intervention is required. In practice, Wiseman's role is to make the calls when automation isn't enough, to read the spacecraft's behavior, communicate with mission control, and make real-time decisions with incomplete information at 250,000 miles from home. He is exactly the kind of person you want making those decisions. Pilot Victor Glover Jr., born in Pomona, California, a U.S. Navy captain, a veteran naval aviator and test pilot who flew the F/A-18 Hornet, the Super Hornet, and the EA-18G Growler electronic warfare aircraft that require a particular kind of technical precision because their job is to blind enemy radar while surviving in defended airspace. Glover logged more than 3,500 flight hours across more than 40 aircraft types. In 2020, he was the pilot on the first operational crewed SpaceX Dragon mission to the International Space Station, the Crew 1 mission, becoming the first black astronaut to complete a long-duration assignment aboard the ISS, spending 6 months in space. Now, on Artemis II, Victor Glover becomes the first person of color to travel to the vicinity of the moon. There is a phrase people sometimes use to describe historical moments like this, and I want to use it carefully because it's true. This is the first time in the 65-year history of human spaceflight that a person of color has traveled beyond the protective magnetic field of Earth, beyond low Earth orbit to another world. Not because of affirmative action or box checking, because Victor Glover is among the most qualified people alive to pilot a spacecraft to the moon, and because the program finally exists to give him that assignment. The symbolic weight of this is real. In a country where the history of space exploration is intertwined with a history of racial exclusion, where brilliant black engineers and mathematicians at NASA were literally segregated into different computing pools until the mid-20th century, where the story immortalized in the book and film Hidden Figures represents not an exception but a rule, Victor Glover going to the moon is a statement about time, about what becomes possible when the doors open, about the cost of waiting. Mission specialist Christina Koch, an electrical engineer and physicist by training, selected as a NASA astronaut in 2013. A researcher who, in 2019 and 2020, spent 328 consecutive days aboard the International Space Station, the longest single spaceflight by any woman in history, breaking the previous record by more than a month. She participated in the first all-female spacewalk in history, alongside astronaut Jessica Meir, in October 2019. She has spent total nearly a year of her life in microgravity. On Artemis II, Christina Koch becomes the first woman to travel beyond low Earth orbit. Not the first woman in space, that was Valentina Tereshkova, Soviet cosmonaut, in 1963. Not the first American woman in space, that was Sally Ride in 1983. Not the first woman to command a space mission. Not the first woman to spacewalk. But the first woman, in the entire 63-year continuous history of human spaceflight since Gagarin, to leave the gravitational neighborhood of Earth entirely. 63 years of space exploration. More than 600 individual humans have traveled to space since 1961. Not one of them, not one, was a woman who went beyond low Earth orbit. Until Christina Koch. Until now. Mission specialist Jeremy Hansen, 50 years old, a colonel and former CF-18 fighter pilot in the Canadian Armed Forces. selected as an astronaut by the Canadian Space Agency in 2009, in a class that included only himself and one other person, out of more than 5,300 applicants. He spent years working at NASA's Johnson Space Center in Houston, supporting astronaut training and mission operations, learning the systems, waiting for an assignment that finally came in April 2023. Artemis II is Hansen's first spaceflight. He has never been to space before, and his first spaceflight is around the moon. Hansen will become the first non-American to travel to the moon and the first Canadian to leave low Earth orbit. He represents an agreement between Canada and the United States that granted the Canadian Space Agency a seat on Artemis II in exchange for Canada's contribution of the Canadarm3 robotic system, which will eventually operate on the lunar surface and support future missions in the vicinity of the moon. He is a living embodiment of the international architecture that makes Artemis different from Apollo, a coalition program rather than a national sprint. He is also, by all accounts, someone who spent a career preparing for exactly this, with the quiet patience of a person who knew the mission would eventually come if the program held together. "The four of us, we are ready to go," Commander Wiseman told reporters at a pre-launch media briefing. "The team is ready to go. The vehicle is ready to go." They were. The physics of the journey is breathtaking in its precision, and I want to walk you through it properly, because the trajectory of Artemis II is not just a path from A to B. It is an elegant exploitation of gravitational mechanics that the ancient Greeks would have found miraculous and that Isaac Newton would have recognized immediately. After launch, Orion spent approximately 1 day in a highly elliptical Earth orbit, ranging from about 185 kilometers at its lowest point to roughly 2,200 kilometers at its highest. This high Earth orbit served several purposes. First, it gave the crew time to check out all of Orion's systems in the actual space environment before committing to the trajectory that would take them to the moon. Second, it positioned the spacecraft correctly for the next critical maneuver. During this first orbit, the crew also performed the proximity operations demonstration, a test in which they manually flew Orion in close formation with the spent interim cryogenic propulsion stage, the rocket's upper stage that had already done its job and was now drifting in orbit. This exercise is about more than just demonstrating manual piloting capability. Future Artemis missions will need to rendezvous and dock with other spacecraft in deep space, potentially with lunar landers, potentially with other modules. Artemis II's proximity operations test was the first real-world data point for how Orion handles in that operational mode with a human at the controls. The crew restored the spacecraft's toilet to normal operations during this time, after a brief period when a fault light appeared during checkout. Christina Koch, with characteristic humor, later called herself the space plumber and declared the toilet probably the most important piece of equipment on board. She is not wrong. The Universal Waste Management System, NASA's name for the toilet, is a marvel of engineering that handles the biological realities of 4 humans in microgravity for 10 days. A system that fails at 200,000 miles from Earth is not a minor inconvenience. It is a mission-threatening emergency. On Day 2, April 2nd, 2026, came the moment that will define this mission in the history books: the translunar injection burn. At 7:49 p.m. Eastern, the European Service Module's main engine ignited. The burn lasted 5 minutes and 50 seconds. At the moment of engine cutoff, Orion was no longer in Earth orbit. The spacecraft was on a trajectory toward the moon, a parabolic arc through space that would carry it 250,000 miles from Earth around the far side of the moon and back. The trajectory is designed so that even without any additional propulsive maneuvers, lunar gravity and Earth gravity acting together would eventually bring the spacecraft back to Earth. This is the free return component of the free return trajectory. It is an escape hatch, a built-in safety net that means a spacecraft traveling to the moon is never truly stranded there as long as the gravity of the moon and Earth continue to work as advertised. Which they will, because they are the moon and the Earth, and they have been reliably massive for approximately 4.5 billion years. The moment the TLI burn completed, the 4 astronauts aboard Orion became the first humans to leave Earth orbit since the crew of Apollo 17 departed lunar orbit and headed home in December 1972. For 53 years and roughly 4 months, no human being had been on a trajectory that took them away from Earth's orbit. Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen crossed that threshold at approximately 7:55 p.m. Eastern on April 2, 2026. Imagine being in mission control in Houston when that call came in. The flight controller at the propulsion console confirming engine cutoff. The guidance officer confirming trajectory nominal. The flight director saying the words that this generation of controllers had trained their whole careers to say, TLI successful. Crew is on their way to the moon. History has texture. That texture sometimes feels like holding your breath for 53 years and finally letting it out. Now, the question that non-engineers always want answered, what does the journey actually feel like? What is it like to be inside this spacecraft traveling to the moon? The honest answer is that we have very good reporting on this from the crew themselves, because Orion has communications capabilities that the Apollo spacecraft could only dream of. The Artemis II optical navigation system, ONS, uses laser communications to transmit data at vastly higher bandwidth than the traditional radio frequency systems. As of day 4 of the mission, this system had already transmitted more than 100 gigabytes of data back to Earth, including high-resolution photographs. For context, the entire data archive of the Apollo program was measurable in kilobytes. The Artemis II crew transmitted the equivalent of thousands of Apollo program data records in 4 days. This means we have real-time video, real-time audio, and those stunning photographs that have been circulating since the mission launched. Commander Wiseman told reporters on day 2 that he could see the entire globe of Earth from pole to pole through Orion's windows, the whole planet, framed in a single view. I don't know what we all expected to see, he said, but you could see the entire globe from pole to pole. Think about what that means cognitively. You are not looking at a landscape. You are not looking at a horizon. You are looking at an object, a thing that happens to be the only home your species has ever known, and it fits in the frame of a spacecraft window. Every human being you have ever met. Every city, every ocean, every mountain range. Your parents' house. The hospital where you were born. The school where you learned to read. The street you walk down every morning. All of it, compressed into a sphere that your hand could cover if you held it up to the glass. Astronauts have described this experience since the very beginning of the space age. There is even a name for the psychological transformation it produces, the overview effect. The term was coined by space philosopher Frank White in 1987, drawing on interviews with dozens of astronauts who described a sudden, powerful shift in perspective when they saw Earth from space. The borders between nations become invisible. The fragility of the biosphere becomes viscerally apparent. The pettiness of human conflict becomes starkly obvious against the backdrop of the void. The overview effect at 250 miles from Earth ISS altitude is powerful. The overview effect from 250,000 miles away, as the Earth shrinks from a globe to a sphere to a circle to a dot, is something qualitatively different. Something for which we don't yet have a fully adequate vocabulary, because no one in the modern era of communication technology, with cameras and live video links and the internet to share everything instantly, has experienced it from this distance. The Apollo astronauts described it, but their descriptions came after the mission, in interviews and memoirs, filtered through memory and the conventions of the stoic military test pilot culture from which most of them came. Wiseman, Glover, Koch, and Hansen are describing it in real time. Their words and images are reaching Earth within milliseconds. We are experiencing their journey with them at a remove of 250,000 miles in something close to real time. On day 4, pilot Victor Glover took manual control of Orion for a deep space handling test, 41 minutes of precision maneuvering to evaluate the spacecraft's response characteristics in the deep space environment, testing both 6 degrees of freedom and 3 degrees of freedom thruster control modes. This is the kind of data that spacecraft engineers spend years waiting to get. The difference between how a spacecraft handles in simulation and how it handles in reality, in actual deep space, with actual microgravity and actual thermal gradients and actual radiation, that difference is irreducible. You cannot simulate it fully on the ground. You can only know it by going. Between these engineering milestones, the crew has been exercising, sleeping, eating, and being human. The exercise program deserves a moment because the engineering behind it is remarkable. The standard exercise equipment on the International Space Station weighs more than 4,000 pounds and occupies about 850 cubic feet of volume. The ISS needs this equipment because astronauts stay there for months at a time, and muscle atrophy and cardiovascular deconditioning in microgravity are serious medical problems, Not just discomforts, but genuine physical hazards that can impair a crew's ability to function after they return to Earth. Orion doesn't have the space for thousands of pounds of exercise hardware. Deep space missions will eventually be much longer than 10 days, and maintaining crew health across months of deep space travel requires solutions that don't exist yet in the ISS paradigm. The solution on Artemis II is a compact flywheel device about the size of a carry-on suitcase, weighing 30 pounds, that uses a cable-based resistance mechanism operating like a sophisticated yo-yo. The resistance you feel is proportional to the force you apply, and it can replicate loads up to 400 pounds. Rowing, squats, deadlifts, upper body work. All of it in a device you could put in an overhead compartment on a commercial flight. This technology will matter enormously for Mars missions. A trip to Mars takes approximately 7 months each way. During those 14 months of transit time, plus time on the surface, astronauts will need to maintain their cardiovascular fitness, muscle mass, and bone density. The solution cannot weigh thousands of pounds, cannot take up hundreds of cubic feet. The flywheel device being tested on Artemis II is a proof of concept for the kind of compact, efficient exercise hardware that will sustain the health of the first humans to travel to another planet. The food is worth mentioning too, because it is humanizing in a way that raw technical details sometimes aren't. NASA published the Artemis II crew menu on March 4, 2026. The crew participated in pre-flight taste tests to select what they wanted to eat. During launch and re-entry, they consume only ready-to-eat foods. In orbit, they can rehydrate freeze-dried meals using Orion's water dispenser and heat items with a briefcase-sized food warmer. The menu includes 58 tortillas. Tortillas have been the bread of choice for space stations since the shuttle era, because a tortilla doesn't produce crumbs, and crumbs in microgravity float into equipment and air filters and crew members' lungs. The menu also includes vegetable quiche, barbecued brisket, and spicy green beans. There are 43 servings of coffee because even in deep space, humans apparently need caffeine. 5 varieties of hot sauce. Condiments including maple syrup in recognition of the mission's Canadian crew member Jeremy Hansen. The maple syrup is, in its small way, a statement about internationalism. About the fact that this is not just an American mission. About the fact that exploration is more interesting and more sustainable when it is shared. The crew was also woken up on day 4 by the song Pink Pony Club by Capsule Roan. This is a NASA tradition going back to the Space Shuttle era. Mission Control selects a song to wake each crew member on each morning of the mission. The tradition began informally and became an institution, a moment when the immense technocratic machinery of spaceflight pauses to play someone a pop song. The crew floats in their sleep pod. The song plays through the spacecraft speakers. For a few seconds, 200,000 miles from Earth, an astronaut listens to music. I find this impossibly human. There is a version of deep space exploration that is pure engineering, numbers, vectors, propellant budgets, abort modes. And there is a version that is also this: barbecued brisket and Capsule Roan and maple syrup for the Canadian. The two versions exist simultaneously, and the simultaneity is the point. We go to the moon because we are brilliant engineers. We also go because we are curious animals who put hot sauce in zero gravity and cry when we see Earth from a great distance. Both things are true. Both things are important. There is a payload aboard Orion right now that might be the most important single item on the entire mission from a scientific standpoint, even though it gets far less attention than the view from the windows. Avatar, a virtual astronaut tissue analog response. This is a system that contains what are called organ-on-a-chip devices, engineered microfluidic platforms that use real human cells cultured in configurations that mimic the behavior of actual human organs. Bone marrow cells derived from the crew's own blood samples are among the biological materials being studied. The system can mimic the functional behavior of individual astronaut organs, lung tissue, gut tissue, heart tissue, under controlled conditions that replicate the deep space environment. Why does this matter? Because the deep space radiation environment is the single largest biomedical challenge facing human exploration beyond low Earth orbit, and we cannot solve it from the ground. Here is the problem in simple terms. Earth is wrapped in a magnetic field generated by its churning iron-nickel core. This magnetic field deflects most of the charged particle radiation that streams constantly from the Sun and from galactic sources, cosmic rays produced by supernovas and other energetic astrophysical events across the Milky Way. The International Space Station orbits at an altitude of about 400 kilometers, still well within this magnetic field. ISS crews receive radiation doses, but they are partially shielded by Earth's protective envelope. Beyond that envelope, beyond the Van Allen radiation belts, out in the space between Earth and Moon, in the territory where Artemis II is currently traveling, the radiation environment is categorically different. Galactic cosmic rays are high-energy particles, primarily protons, helium nuclei, and heavier nuclei, that have been accelerated to enormous energies by distant astrophysical events. They travel at speeds approaching the speed of light. They penetrate spacecraft walls. They penetrate human bodies. They can break chemical bonds in DNA. They can damage the central nervous system in ways that produce cognitive effects, reduce spatial reasoning, impaired memory consolidation, altered decision-making. Solar energetic particles, bursts of charged particles ejected from the sun during solar flares and coronal mass ejections, can deliver acute radiation doses that are dangerous on timescales of hours. During the Apollo era, the astronauts were lucky. None of the missions coincided with a major solar particle event while crews were in deep space. If Apollo 16, for instance, had launched 3 months earlier, the crew might have been caught in a major solar storm while traveling between Earth and Moon. The outcome could have been very different. For a Mars mission, luck is not an acceptable mitigation strategy. A Mars crew will spend 7 months in transit to Mars, time on the surface, and 7 months in transit back, roughly 20 months total, during which there is no possibility of rapidly evacuating to a protected environment. The cumulative radiation dose from galactic cosmic rays alone, across a full Mars mission, exceeds the career radiation exposure limits that NASA currently sets for astronauts. Solving this problem requires understanding, at the cellular and organ systems level, exactly what deep space radiation does to human biology. Avatar is one piece of that understanding. The organ-on-a-chip devices experience the same radiation environment as the crew, while being monitored continuously for biomarker changes that indicate cellular stress, immune response, and organ dysfunction. This is the first time Avatar has operated outside the International Space Station and outside the Van Allen belts. The data it generates from this mission will be a foundational dataset for every deep space biomedical research program that follows. Artemis research for crew health and readiness is the complementary system. The crew members are wearing movement and sleep monitoring devices before, during, and after the mission. Sleep patterns in deep space, cardiovascular rhythms, movement efficiency, cognitive performance metrics. All of this data is being collected in real time and will be available to researchers studying the long-term effects of deep space travel on human health. The German Space Agency contributed multiple M42 radiation sensors installed inside Orion, measuring the radiation field within the crew cabin at multiple locations simultaneously. This gives researchers a three-dimensional picture of how radiation penetrates the spacecraft and distributes through the inhabited volume, critical data for designing future spacecraft with optimized radiation shielding. These experiments, Avatar, Archer, the German radiation sensors, several others, are not secondary activities tucked into spare crew time. They are core mission objectives. Artemis II is simultaneously a systems test flight for Orion and SLS, a pathfinding mission to restore human deep space capability, and a biomedical research platform generating data without which we cannot responsibly plan the next generation of human spaceflight. The Moon is the destination of record for Artemis II, but Mars is the destination of aspiration for the entire program. And every data point collected by every sensor aboard Orion right now is a building block toward the day when a crew of 6 humans fires up a rocket in Earth orbit and begins the 7-month journey to the Red Planet. Let's talk about the CubeSats. They don't get much attention in the main mission narratives, but they are important. 5 small CubeSat satellites, roughly the size of shoeboxes, were carried aboard Artemis II, selected from nations that are signatories to the Artemis Accords. They deployed after Orion separated into high Earth orbit, and they are now conducting independent scientific missions. Germany's Tacheles is examining the impact of deep space conditions on electrical components used in lunar vehicles. A direct engineering investigation into how the hardware that future rovers and lunar surface systems will depend on actually behaves in the radiation environment beyond Earth's magnetic field. Argentina's Atenia is studying radiation shielding strategies. These are small missions, The investment relative to the cost of the main mission is tiny, but they represent something culturally significant: the democratization of deep space access. 61 nations have signed the Artemis Accords as of early 2026, committing to a set of principles for peaceful, transparent space exploration. Not every nation can build an Orion capsule. Not every nation can build an SLS rocket. But every nation that has signed the Accords is, in principle, a potential participant in the program, contributing sensors, instruments, expertise, infrastructure. This is different from Apollo. Apollo was fundamentally a unilateral American program, conducted with some international coordination but without genuine international partnership in the hardware and operations. Artemis is structurally a coalition, with the European service module that powers Orion built by Airbus in Bremen, the Canadarm3 that will one day operate near the moon built by Canadian industry, the science instruments contributed by space agencies from Japan to Australia to Italy. The Artemis Accords, the framework of principles governing this coalition, establish norms for transparency in space exploration, interoperability of systems, sharing of scientific data, and the protection of historically significant lunar sites. They are not a legally binding treaty. They are a statement of intent and mutual commitment, and they have attracted signatures from across the world, though notably not from Russia or China, both of which have described the Accords as an attempt by the United States to write international space law to its own advantage. The geopolitics are real and they are significant. China's Chang'e program has achieved remarkable results, landing robotic spacecraft on the lunar far side, returning samples to Earth, making steady progress toward a crewed lunar landing that Chinese officials have indicated they are targeting for around 2030. The lunar South Pole, where Artemis is targeting for the first crewed landing in the Artemis IV mission, is also where China intends to establish a presence. The permanently shadowed craters at the lunar South Pole, which have never been exposed to direct sunlight since they formed billions of years ago, are believed to contain substantial deposits of water ice. And whoever establishes sustained operations there will have access to a resource of extraordinary strategic value for deep space exploration. Water ice at the lunar South Pole can be mined and processed. Electrolysis, splitting water into hydrogen and oxygen using electrical power, converts it into rocket propellant. A rocket fueling operation at the lunar South Pole would turn the moon into not just a destination, but a gas station on the highway to Mars and beyond. This is the vision that makes the Artemis program something more than a repeat of Apollo. The goal is not to plant flags and collect rocks and come home. The goal is to establish the infrastructure for sustained human presence in the Earth-Moon system, using lunar resources to support missions further into the solar system. The moon as a base camp for the solar system, a way station, proving ground, a place where humans learn to live in low gravity, in high radiation, in the absence of the thick atmospheric cocoon they evolved in, before they attempt the same in the thinner margins that Mars will offer. There is a zero-gravity indicator floating inside the Orion crew cabin right now, tethered to a wall by a short cable, bobbing gently in the recirculated air of the spacecraft's life support system. This is a NASA tradition going back to the space shuttle era. Every crewed mission carries a small floating object, visible on camera, a quick visual confirmation for ground controllers, and the public that the spacecraft has reached weightlessness. Previous missions have carried everything from small stuffed animals to mission patches to custom figurines. For Artemis I, the uncrewed test flight, the zero-gravity indicator was a small plush Snoopy wearing an orange flight suit. For Artemis II, NASA held a public design contest. They received 2,600 submissions from more than 50 countries. Children, students, engineers, artists, all of them invited to contribute to this small tradition, this tiny talisman that flies with the crew. The winner was an 8-year-old boy named Lucas Yee from Mountain View, California. His design is called Rise, inspired by the photograph of Earthrise taken by Apollo 8 astronaut William Anders in December 1968. It depicts the moon wearing Earth as a baseball cap. The moon wearing Earth as a baseball cap. Designed by an 8-year-old. It was fabricated by NASA, attached to a tether, and placed inside the Orion crew cabin before launch. It is currently floating at approximately 200,000 miles from Earth, in a spacecraft traveling toward the moon. An 8-year-old's imagination, his vision of the relationship between Earth and moon, expressed in a playful, slightly whimsical object, is physically present in deep space right now. It will travel around the moon. It will return to Earth. It will be one of the artifacts of this mission. I keep coming back to this. Not because it's the most technically significant aspect of Artemis II, clearly it isn't, but because it says something true about why we go to space that the orbital mechanics and the propellant budgets and the radiation dosimetry alone cannot say. We go because it captures the imagination of 8-year-olds. We go because children draw the moon wearing Earth as a hat, and that image is exactly right, somehow. We go because the species that does this, that sends a child's drawing to the moon, is the same species that builds the machine to send it there. The wonder and the engineering are not separate things. They are the same thing at different levels of resolution. Tomorrow, Monday, April 6th, 2026, is the day the mission has been building toward, the lunar flyby. The flyby window runs from approximately 2:45 p.m. to 9:40 p.m. Eastern Daylight Time. During this roughly 7-hour period, Orion's main cabin windows will be oriented toward the moon, and the crew will be close enough to the lunar surface to make detailed scientific observations. The closest approach, the moment of minimum distance between Orion and the moon, occurs at approximately 7:02 p.m. Eastern, at a distance of 4,066 miles from the lunar surface. 4,066 miles sounds like a long way, but consider this: the Apollo missions flew their orbital passes approximately 70 miles above the lunar surface. They were close enough to see individual craters and mountains in tremendous detail, but they were inside the moon's gravity well, orbiting. Artemis II's flyby trajectory keeps the spacecraft further out, 4,066 miles at closest approach. But from that distance, the crew will be able to see the entire disk of the moon at once. Near side and far side, both poles. The full globe of the moon in a single view, the way Earth looks to them from 200,000 miles away. That is a perspective no Apollo crew ever had. They were too close, orbiting too low, to see the whole thing at once. The lunar science team, led by NASA's Goddard Space Flight Center and coordinated from the Science Evaluation Room in Mission Control at Johnson Space Center in Houston, has spent weeks building the Lunar Targeting Plan. This is a detailed guide to what the crew will observe and photograph during the flyby window. The science team includes specialists in impact cratering, volcanism, tectonic features, and lunar ice. They will be in real-time contact with the crew, providing guidance on what to look for as surface features scroll past the windows. The science targets include craters, ranging from fresh impact craters that formed relatively recently and show preserved ejecta blankets to ancient craters that have been modified by subsequent bombardment and geological processes. Ancient lava flows, the dark basaltic plains that fill the large impact basins on the near side of the moon. Tectonic features, the ridges and scarps that formed as the moon's crust slowly contracted as the interior cooled over billions of years. And the Oriental Basin. The Oriental Basin is 600 miles across. It is one of the largest and best-preserved multi-ring impact basins in the solar system, the kind of structure that forms when a very large impactor, perhaps 40 or 50 kilometers across, strikes a planetary body at extreme velocity and the shockwave propagates outward through the crust, creating a series of concentric rings like the rings on a bullseye hundreds of miles in diameter, frozen in rock. The Oriental Basin marks the transition zone between the near side and far side of the moon. It sits at the western limb of the moon as seen from Earth, just barely visible from Earth under ideal conditions, and only as a dim pattern at the edge of the disk. Its interior is mostly on the far side, and until the age of spacecraft imagery, its full structure was unknown. Robotic spacecraft have imaged Oriental from orbit. The Lunar Orbiter program in the 1960s. The Lunar Reconnaissance Orbiter more recently. The Chinese Chang'e missions. But no human eye has ever observed the Oriental Basin directly, from nearby, in the natural colors and textures that only human vision in real space can perceive. The first image of the moon taken by the Artemis II crew already showed a portion of the Oriental Basin on the left side of the frame. Human eyes, on a camera attached to a spacecraft window, seeing something that has only been seen by robot cameras before. A first, unremarked by most news coverage, but noted quietly by lunar scientists who have spent their careers studying this basin from a distance. During the flyby, the crew will see far more. and they will describe it in real time to the science team in Houston. Then, approximately 1 hour after Earthrise, the solar eclipse. When Orion reaches the far side of the moon at closest approach, Earth will be on the other side, behind the moon from the spacecraft's perspective, and then, as the trajectory carries Orion around the far side and out the other side, Earth will rise over the lunar horizon. Earthrise. The original Earthrise photograph, taken by William Anders aboard Apollo 8 on December 24, 1968, is one of the most reproduced images in human history. Environmental historian Galen Rowell called it the most influential environmental photograph ever taken. The image of Earth, blue and white and achingly fragile, rising above the gray lunar surface, surrounded by absolute black, communicated something about the relationship between humanity and its home world that no words had managed to communicate as effectively before. The crew of Artemis II will experience Earthrise in person. Not through a camera viewfinder in the 1968 sense, but through a spacecraft window, with the communications technology to share the experience in real time with everyone on Earth who is watching. And then, 1 hour after Earthrise, Earth will pass between the spacecraft and the Sun. From Orion's position around the far side of the moon, Earth will align with the Sun from the crew's perspective. The solar disk, 865,000 miles in diameter, 93 million miles from Earth, will be blocked by Earth, which is 7,917 miles in diameter and 250,000 miles from the spacecraft. The geometry works out to an eclipse, and that eclipse will last approximately 53 minutes. For 53 minutes, the crew of Artemis II will watch their home planet as a burning ring of light. The atmosphere, that thin blue haze that makes Earth livable, that fraction of a percent of the planet's radius that contains all the weather and all the oxygen and all the biological activity of the most biodiverse world we know of, will glow in the sunlight bending around Earth's edges. The scientific term for this is atmospheric limb scattering. The experiential term for it is something close to divine. Imagine being in that spacecraft. You have just watched Earth rise over the lunar horizon, your home world, reduced to a sphere, now rising like a moon over the moon. You have been living and working in a pressurized capsule for 4 days, eating barbecued brisket and drinking rehydrated coffee, running experiments, troubleshooting minor systems glitches, getting woken up by pop music. And then Earth rises and the scale of what you are doing rushes in. And then an hour later, Earth eclipses the Sun. And you are the first human being to see this since the crew of Apollo 17, and actually in a trajectory that lets you see it this clearly, perhaps the first human being to see this at all in this specific way, from the specific vantage point this far on the far side of the moon. There are no adequate words for that. There are only the inadequate words that people have been reaching for since the first time an astronaut looked back at Earth and tried to describe it. The overview effect. The pale blue dot. Carl Sagan's meditation in 1994 on the Voyager 1 image taken from 3.7 billion miles away, when Earth appears as a fraction of a pixel in a band of scattered sunlight. But those were observations from very far away, filtered through cameras and transmitted across years. The Artemis II crew is doing something different. They are there, human bodies in a spacecraft experiencing with their biology the thing that all the photographs and descriptions have been trying to convey. And they are sharing it with us in real time across the void. Let me tell you about what the mission found that it wasn't looking for, because this is where exploration always exceeds the mission plan. On the third day of the mission, April 3rd, the crew reported a mild, unusual smell inside Orion. Nothing that triggered a safety alert. Nothing that indicated a hardware failure. Just a smell noted by the crew, reported to mission control, investigated by flight controllers. Deputy Program Manager Debbie Korth addressed it directly at a news conference, demonstrating the operational transparency that modern NASA has worked hard to build after the cultural failures that contributed to Columbia and Challenger. The investigation found nothing anomalous in the power data or the heater data. The smell was traced, tentatively, to off-gassing from tape and other materials, a known phenomenon in new spacecraft, where various adhesives and coatings emit trace chemical compounds in the first days of operation. A similar smell had been reported on the ground during testing. Engineers concluded it was likely mechanical in nature and not a safety concern. This is how operational spaceflight actually works. There are always anomalies. The systems are extraordinarily complex. and the environment is unlike anything on Earth. Something smells different than expected, and you investigate it, you report it transparently, you characterize it, and you keep flying if the analysis supports doing so. The public transparency of this process. A deputy program manager standing at a podium and walking through the smell investigation in real time is itself a cultural artifact of a program that has worked hard to build and maintain an engineering culture where anomalies are reported rather than managed silently. The crew also dealt with a brief issue with the spacecraft's wastewater management system on day 4. A venting line that wasn't clearing properly. Engineers used heaters to address potential ice blockage and oriented the vent toward the sun for thermal assistance. The toilet was operational. The crew was briefly asked to use backup collection devices as a precaution. The issue was being investigated. These are the unglamorous realities of deep space exploration. The poetic and the plumbing coexist. You are the first woman in history to travel beyond low Earth orbit, and you are also troubleshooting the waste management system. You are the first person of color to travel to the vicinity of the moon, and you are also running the acoustics test that will help engineers understand sound levels in the crew cabin. The history-making and the checklists exist simultaneously in the same spacecraft on the same days. This, too, is what exploration looks like. It is what it has always looked like. Lewis and Clark didn't sail through pristine wilderness experiencing continuous transcendence. They were mostly wet and cold and sick and running low on supplies. Shackleton's crew didn't float serenely through the Antarctic. They were stranded on ice floes for months, rowing lifeboats in freezing storms, eating whatever they could find. The sublime and the ordinary are inseparable in the history of exploration. Artemis II is exactly in that tradition. The return journey begins after the lunar flyby. Once Orion swings around the far side of the moon and the science observations are completed, the spacecraft will begin the multi-day coast back toward Earth. The precise timing of the return burns will depend on the actual trajectory data from the flyby. Mission Control will compute the exact burns needed to bring Orion back to an Earth entry corridor with the precision required for the skip reentry profile. The skip reentry is worth explaining, because it is different from the Apollo-style direct re-entry and is one of the engineering changes made in response to the Artemis I heat shield analysis. During a direct re-entry from a lunar trajectory, the Apollo approach, the spacecraft enters the atmosphere at approximately 25,000 miles per hour and descends steeply through the atmosphere, with the heat shield generating temperatures of up to 5,000 degrees Fahrenheit as atmospheric friction slows the spacecraft. The Apollo capsules accomplished this in a single continuous entry that lasted about 15 minutes from atmospheric interface to parachute deployment. Artemis II will use a shorter skip re-entry. The spacecraft will enter the upper atmosphere, use the lift generated by Orion's asymmetric shape to skip back out of the atmosphere briefly, like a stone skipping across water, and then re-enter for the final descent. This approach has two advantages. It reduces the peak heating rate on the heat shield, because the first atmospheric skip dissipates some of the entry energy before the final descent, and it provides more precise control over the splashdown location, which makes recovery operations more predictable. The skip reentry is also the component of the mission that was most carefully analyzed in the wake of the Artemis I heat shield finding. The specific reentry profile, the angle, the duration of the first skip, the duration of the second entry, was optimized to stay within the performance margins that the heat shield analysis confirmed. It is a tighter profile than Artemis I's reentry, but that tighter profile is precisely what the analysis required. After reentry, the drogue parachutes will deploy at approximately 25,000 feet altitude, slowing the capsule from roughly 325 miles per hour to about 135 miles per hour. Then the three main parachutes, each 116 feet in diameter, will deploy and slow the capsule further. At splashdown in the Pacific Ocean, the vertical velocity will be approximately 20 miles per hour, about the speed of a person jogging. The capsule will hit the water, stabilize, and float. Navy divers and recovery personnel will be on scene within minutes. The crew will be extracted. The spacecraft will be recovered. And 4 human beings will have completed the first crewed lunar flyby mission since December 1972. The question I always anticipate at this point is the hard one. Not the technical questions, those have answers grounded in physics and engineering. The hard question is the philosophical one. The one that underlies every discussion of expensive, dangerous, ambitious human exploration. Why? Why does any of this matter? We have problems on Earth. Climate change is rewriting the conditions of human civilization. Hundreds of millions of people lack clean water, adequate food, basic medical care. Political systems are under stress in ways that feel historically unprecedented. The infrastructure of civilization, roads, bridges, power grids, water treatment facilities, is aging and underfunded across the developed world. Why, in the face of all of this, does it make sense to spend money sending for people to fly around the moon? I want to offer several answers to this, because there isn't one answer. There are many operating at different levels of analysis. The first is economic. Space exploration generates technology. This is not a rhetorical talking point. It is a documented, quantifiable historical fact. The Apollo program is estimated to have generated more than 6,300 spin-off technologies that found applications in everyday life. Memory foam mattresses were developed for astronaut seats. The technology behind modern CAT scans traces back to imaging systems developed for the Lunar Orbiter program. Water filtration systems used in developing countries today trace back to NASA water purification research. Cordless power drills were developed to drill into moon rock. Computer chips were miniaturized under pressure from the demands of the guidance computers that had to weigh less than a kilogram and perform more calculations per second than anything that had existed before. The Artemis program is generating the next generation of these technologies. Compact exercise systems for long-duration space missions will eventually find their way into physical therapy clinics and cardiac rehabilitation programs. Radiation monitoring systems developed for deep space will improve radiation dosimetry for cancer patients and radiation workers. Life support systems designed to sustain 4 people indefinitely in a closed environment will advance the technology of air and water recycling systems that are relevant to sustainable terrestrial infrastructure. Communication systems using laser light to transmit enormous data volumes across vast distances will shape the future of telecommunications. These are not speculative claims. They are patterns of technology transfer that have repeated consistently throughout the history of space exploration. The second answer is scientific. The Moon is a 4.5 billion-year-old time capsule. Unlike Earth, which has an active geology that continuously recycles its surface through volcanism and plate tectonics and erosion, the Moon's surface preserves a record going back to the earliest days of the solar system. The rocks that the Apollo crews brought back from the equatorial nearside have told us enormous amounts about the early bombardment history of the inner solar system. The lunar South Pole, the target of Artemis II and future missions, is even older, and the permanently shadowed craters there may contain water ice that formed during the early solar system and has been preserved at cryogenic temperatures for billions of years. Ice that may record the chemical composition of the early solar system, including the building blocks of life. We have one planet that we know has life. We are increasingly finding that the ingredients for life, water, carbon compounds, organic molecules, are common throughout the solar system. The question of whether life is rare or common in the universe is one of the most profound questions the human mind has ever formulated. The answer to that question may lie, in part, in the chemistry of ancient ice at the lunar South Pole. The Artemis program is the first systematic effort to go there with the tools and the presence to find out. The third answer is strategic. The Moon is, in the 21st century geopolitical context, a contested domain in a way that it wasn't during Apollo. China's space program is serious, well-funded, and making steady progress. Chinese officials have stated that their goal is a crewed lunar landing by 2030 and a permanent presence at the lunar South Pole. The United States, through Artemis, is pursuing the same geography. The Outer Space Treaty of 1967 establishes that no nation can claim sovereignty over the Moon, but it does not prevent the establishment of operational presences that could effectively control access to specific resources. Water ice at the lunar South Pole is the most valuable resource in near-Earth space if we are serious about human exploration beyond the Moon. Whoever establishes sustained operations there first will have a significant strategic advantage in the long term of solar system exploration. The fourth answer is the one that I find most compelling, and it is the hardest to quantify. The fourth answer is perspective. Every time a human being has traveled far enough from Earth to see the whole planet at once, something has happened to them. Something has happened to the people who heard their descriptions and saw their photographs. The overview effect is real. The pale blue dot is real. The experience of seeing Earth as a thing, a small, luminous, fragile thing in an enormous black void, does something to the human mind that cannot be produced by any other means. We are living in an era of extraordinary political fragmentation, of tribal identification and zero-sum competition, of a deep cultural sense that we and they are the relevant categories for organizing reality, and that they are always the problem. The moon doesn't care about any of that. Space doesn't organize itself along national lines. The void is the same void, whether you approach it from Cape Canaveral or from the Baikonur Cosmodrome. The Earth looks the same from the far side of the moon, whether you are an American or a Canadian or a person from any nation that has ever looked up and wondered. When for human beings look out the window of Orion tomorrow and see Earth eclipsed by the sun, when they see their home world as a glowing ring of atmospheric light against the black, they will be having an experience that is, as nearly as we can make it, a universal human experience. Not an American experience. Not a military experience. Not a government experience. An experience that belongs to the species because it is the species that built the rocket, the species that wrote the orbital mechanics, the species that made the tortillas and the maple syrup and the coffee that the 4 people floating in that capsule are consuming. Victor Glover is up there because the human species got itself organized sufficiently to train and equip and launch the best people available regardless of the color of their skin. Christina Koch is up there because the human species got itself organized sufficiently to allow women into the rooms where astronauts are selected. Jeremy Hansen is up there because 2 nations decided that cooperation was more valuable than exclusivity. Reed Wiseman is up there because decades of experience and discipline and willingness to do the work produced someone who could be trusted with the most important command in human spaceflight since the Apollo era. All 4 of them are up there because 8-year-old Lucas Ye drew the moon wearing Earth as a baseball hat, and 2,600 other children and artists and engineers from 50 countries submitted their own visions of what it means for humans to travel to the moon. When we say, we are going to the moon, the we is real. It is not a rhetorical device. It is a statement about the species. I want to say something about the timing of this mission, because it is not incidental. The mission launched on April 1st, 2026. The lunar flyby occurs on April 6th. The splashdown in the Pacific is expected around April 10th or 11th. This is happening right now. Not in the past. Not in the future. Right now, as you watch this, as you listen to these words, for human beings are closer to the moon than any human has been since December 1972. We live in a media environment that makes everything feel urgent and everything feel temporary. The news cycle is measured in hours. The attention span for any single event, even an extraordinary one, is compressed by the sheer volume of other events competing for the same finite pool of human attention. A month from now, most of the people who are casually aware that Artemis II launched will have moved on to other concerns. But here is what will not change a month from now, or a year from now, or a century from now. April 6, 2026, for human beings flew around the moon. They saw the far side of the moon with their naked eyes. They watched Earthrise from the vicinity of the lunar far side. They watched Earth eclipse the sun. They went further from Earth than any human had gone since 1972, and they came back. That is in the permanent record of what the species has done. That is written into the history of the civilization as surely as the Apollo landings are written into it, as surely as the Voyager spacecraft passing through the heliopause is written into it, as surely as the first time a human being looked at the moon and wondered if they could go there someday. We are making history right now, not in the rhetorical sense that every generation uses to make their moment feel significant. In the literal, documentable, permanent record sense. The species that built the rocket and the spacecraft and trained the crew and launched them into the void and is watching them right now through laser-linked communications from 250,000 miles away. That species is us, and this is happening. The question of what comes next is worth addressing, because Artemis II is not a destination. It is a waypoint. The roadmap, as of April 2026, looks like this. Artemis III, currently planned for 2027, is a mission designed to demonstrate the commercial lunar landing system in low Earth orbit. This mission will test rendezvous and docking procedures between Orion and SpaceX's Starship human landing system, which will eventually carry astronauts to the lunar surface. Starship HLS still needs to complete an orbital propellant transfer demonstration before it can be human-rated, an operation in which one Starship vehicle in orbit transfers propellant to another, a necessary capability because Starship needs to be refueled in orbit before it can complete the journey to the moon. This is a technically challenging operation that has not yet been demonstrated, and its success is a prerequisite for the crewed lunar landing. Artemis IV, currently planned for early 2028, is the mission intended to land humans on the moon for the first time since Apollo 17. The landing site is in the lunar South Pole region, near the Shackleton crater and the Degerlache crater, in territory chosen specifically because it offers access to permanently shadowed regions believed to contain water ice, while also having areas of near-permanent sunlight that can power solar energy systems. The crew of Artemis IV will include the first woman and the first person of color to set foot on the lunar surface. These are not science fiction scenarios. They are plans with hardware under construction, with contracts signed, with crews in training. Whether they succeed on schedule depends on a dozen variables: the progress of Starship's development, the continued political support for the program across presidential administrations, the readiness of the international and commercial partners, the results of Artemis II itself. But the foundation is being laid right now. The foundation is Orion, named Integrity, currently traveling toward the moon with 4 people inside it who are demonstrating that the system works, that humans can survive and function in the deep space environment, that the life support and navigation and communications and propulsion systems all operate as designed when the real stakes are in play. Beyond the moon, the vision is Mars. The Moon to Mars program is NASA's organizing framework for everything beyond Artemis. Use the moon to learn how to sustain human life beyond Earth. Use the lunar South Pole as a research station and a propellant depot. Use the data from Avatar and Archer and every biomedical experiment carried on every Artemis mission to understand how the human body adapts to and is damaged by the deep space environment. And then, sometime in the 2030s or early 2040s, commit to the mission that is the ultimate aspiration of the program: a crewed mission to Mars. There are people alive today who will land on Mars. There are children in school right now who will train as astronauts and fly the missions that follow Artemis. There are engineers at SpaceX and NASA and Blue Origin and Rocket Lab and 100 other companies who are building the hardware that will carry those crews. There are scientists at universities and research institutes who are running the experiments, building the databases, solving the biological and engineering problems that need to be solved before those missions can happen. And Artemis II is the link between the last time humans went to deep space, December 1972, and everything that follows. It is the restoration of the capability that was allowed to lapse. It is the proof that the gap is closed. It is the beginning of the era in which human presence in deep space is no longer an extraordinary event but a regular operational activity. Here is something that I think about when I think about what Artemis II means. Somewhere on Earth right now, as of April 5, 2026, the day before the lunar flyby, there is a child who is watching the Artemis II mission coverage. Maybe they are 8 years old, like Lucas Ye, who designed the zero-gravity indicator floating inside Orion right now. Maybe they are 12. Maybe they are 6. They are watching a spacecraft travel to the moon. They are watching for people float in a capsule and describe what Earth looks like from far away. They are watching the moon grow in the images transmitted back. And they are going to remember this. The way that certain people who were children in 1969 remember watching the Apollo 11 landing on a black and white television, not fully understanding what they were seeing but understanding that it was important, that the adults around them were moved by it, that something was happening that would matter for the rest of their lives. That child watching Artemis II right now is going to grow up in a world where humans go to the moon regularly, where the lunar South Pole is an operational outpost, where the question, when will we go to Mars, has a specific answer rather than a vague aspiration. That child may become one of the astronauts who goes to Mars, or one of the engineers who builds the propulsion system for the Mars mission, or one of the scientists who processes the samples brought back from the Martian surface and determines, or doesn't determine, whether life once existed there. Or they may just grow up knowing that the species they belong to is the kind of species that goes to other worlds. That the moon is not just the thing that creates tides and appears in poetry. That it is a place with a surface with craters and lava flows and a vast basin called Oriental that is 600 miles across, and that human beings can go there and come back, and that some of them will one day stay. That knowledge, that orientation, shapes a person in ways that are hard to quantify but real. It shapes what they think is possible. It shapes how they understand the relationship between human intelligence and the physical universe. It shapes whether they look at a problem and ask, "Can this be solved?" or simply assume it cannot. The 12 people who walked on the moon during Apollo inspired a generation. Many of the engineers and scientists who built the Hubble Space Telescope, the Mars rovers, the International Space Station were children who watched Apollo and decided that this was the kind of work they wanted to do. The Apollo missions created the pipeline that made everything that followed possible. Artemis II will do the same. For a new generation with new tools, new perspectives, a more diverse crew, a more international program, a more ambitious long-term vision. There are things happening aboard Orion right now, in the hours before the lunar flyby, that will probably not make the news. The crew is preparing the cabin. They are stowing equipment that doesn't need to be accessible during the flyby observation period. They are reviewing the lunar targeting plan, the detailed observing guide that the science team in Houston has been building since the TLI burn completed 3 days ago. They are checking the cameras and the imaging systems. They are eating dinner. They are floating in a spacecraft that is traveling toward the moon at roughly 2,500 miles per hour, and they are doing what all professional explorers do in the hours before the main event. They are preparing. Victor Glover is scheduled to take manual control of Orion tonight, April 5th, at 9:10 p.m. Eastern, for a deep space handling test. He will fly the spacecraft through a series of precision maneuvers, providing engineers with data about how Orion responds at this distance from Earth, in this radiation environment, with this thermal profile, with these propellant levels. Every decimal point of data from this demonstration will feed directly into the planning for future missions. A 24-hour acoustics test is also ongoing, measuring sound levels at various points inside the Orion crew cabin across the full range of operational modes. Sound in a spacecraft is not trivial. Sustained exposure to elevated noise levels affects sleep quality, communication clarity, and over long missions, hearing health. The acoustics data from Artemis II will be used to design quieter, habitable volumes for future spacecraft. These are the details that don't make headlines.